In our program so far, we have only used variables within the functions in which they were declared. These variables exist on the stack, a location in memory reserved as a workspace for functions. In this module, we will learn about allocating space on another section of memory called the heap. Let's consider this code which defines an integer variable I and a pointer pt that points to I. Nothing new here. We can use the pointer to access the values stored in the integer variable. Now, let's make some changes so that I is allocated and assigned in a function. We'll have the function return a pointer to int, which holds the address of I. Let's compile this version. It produces a warning message telling us that we are trying to return the address of a variable on the stack. This should be enough to tell us that something is wrong. But suppose for a minute that we didn't notice this warning, and we went ahead and ran the program. It appears to work, but there is still a big problem. We just can't see it yet. Let's add another function that seems to have absolutely nothing to do with I or pt. It simply declares an int variable and returns it. And we'll just ignore the return value. So now we'll compile and run this new variation. What are you expecting as the output? Was that what you predicted? Why does calling this seemingly irrelevant function change our value of *pt? Is something wrong with the new function? No, the new function is fine. The problem is with our earlier code. Variable I is declared as an int within the function setI, so it is only available within the function setI. When the function setI runs, memory is allocated on the stack for I. But once function setI returns, the memory is freed, and it can be reallocated for some other purpose. When the second function runs, it reuses some locations in the stack. The same memory location was used for both the variable I and the variable junk. pt was set to the address of I, which is also the address of junk. So when we print the dereferenced value of pt, we see the value 999. This demonstrates that we shouldn't access variables allocated on the stack after they have been deallocated. So how can we allocate memory in a function and have that memory accessible after the function returns? When a program is executing, there is another portion of memory where we can allocate space for variables that have to last beyond the return statement of the functions in which they were declared. We call this area the heap. The function malloc allocates memory on the heap. Heap memory remains available until the programmer explicitly deallocates it. The size parameter indicates how many bytes of memory should be allocated. Its type is size_t, which is a type defined by the standard library as the type returned by sizeof. In general, size_t is an unsigned int. The return type is void star. As you might suspect, this is a pointer. It holds the address of the memory allocated by malloc on the heap. When we learned about pointers earlier in this module, you saw that pointers store the type of the information to which they point. Do you remember why the compiler needs to know this? Remember that pointers should always refer to a legal address for its type. So when we increment a pointer, it is updated to refer to the next legal address. So adding 1 to a char pointer increases the address by 1, the size of a char. But adding 1 to an integer pointer increases the address by the size of an int, which is 4 on my machine. This is important for explicit pointer arithmetic, but also important if the pointer holds the first element of an array. To calculate the address of all the rest of the array's element, the pointer needs to hold the element type information. So what type does void star hold? A void pointer is used to return a pointer of generic type. Malloc returns a void pointer because it doesn't need to know how the memory being allocated is going to be used. It simply allocates size bytes of memory on the heap, as specified by the programmer, and then returns a pointer to that memory. When we store that address in a pointer, the type of the pointer specifies how the memory will be used. Now let's change our function setI to allocate space for I on the heap rather than on the stack. Instead of simply declaring I, we will declare a pointer to I. We'll call malloc and pass it size of int as the parameter so that it allocates enough space to hold one integer. This call returns a void pointer, but we assign it directly to our integer pointer, indicating that we will use the allocated memory as an int. Now we assign 5 to the dereferenced value of ipt. Let's verify what's happening. In set I, space is allocated on the heap, and then the value 5 is placed in our newly allocated heap memory. When some other function is called, it continues to use stack memory. Note that our heap memory is still allocated. Then, when we print the contents of *pt, we get the correct value. In the next few videos, we'll look more closely at malloc and its partner, free.